So today we are going to discuss the topic of second project of CML 661, that is to solve and refine the structures of given drugs using olex2 software by uploading the given HKL and INS file. So in this part of my project I used olex2 as required to solve and refine the crystal structure starting from the experimental diffraction files. So the diffraction files were given as per the structure data, and like these the HKL and INS files were given, and these were to be opened using olex software. It's no, first I'll have to open olex. So I in the olex I have already refined the structure of given RMAL sorry RML file in which I have uploaded the given HKL ins file, and it gave a electron density spheres on the file, and on those spheres we have to refine the atoms from our knowledge, and from this value which was given here, which is the R value, which is the refinement factor, which is sum of F observed minus F calculated divided by the summation of F observed. F is the structure factor, and it is the intensity is proportional to the square of structure factor, and it is the structure factor is already given in the file which was uploaded, and it is for each HKL that is present in the unit cell, and for all reflection that we collect, we calculate the F calculated, and that is why the sum is used to calculate the R factor, because for each HKL there is associated F, and for many thousand reflections that we take, which is uploaded in the file FHKL and INS file, HKL and INS file, so that is why we use the summation. The smaller the value of this R factor, the good the of our structure is in good agreement with the real structure. So I first imported the HKL file which contains the measured diffraction intensities along with the corresponding INS file. It reads that if I upload INS file, it reads that it must have an HKL file also, so they both open simultaneously. That defines the initial instruction for the structure refinement. After loading these files, olex2 automatically generates the initial electron density map, and using this electron densities pattern, I located the atomic positions and gradually built the molecular structure of the compound, and performed a series of refinement cycles in olex2 to improve the atomic parameter, thermal factors, and overall model fit. And once a stable structure was obtained with acceptable R value, which is generally less than 5%, I finalized the model and generated the olex2 report, which includes the crystallographic details, refinement statistics, and OTIP style images of the solved structure. So to quick review, from file I have opened the structure, and from any like this RMAL file I have generated. From after generating the report, once you have to click on the refinement again, you can get the CIF file of the same structure that we have generated. So here HKL and INS file, once you click on it, you can get the electron density diffraction pattern available. It's not giving because I have already solved the structure of this drug. Uh, So I have uploaded the HKL ins file of another drug which was given to us in the form of HCT HKL. We will click on work and solve the structure, and it will start solving it to give us the pattern of electron densities. And here it is not. I have already selected the assigned position of the atom, so it started refining. If we will refine, we can get the R values as here. And it is, as you can see, it is 7. It is another drug. With the drug I have already solved, it was not opening. So if we want to solve it again, we will solve it to get the minimum value of R, and then so now we will learn how we can assign the electron density. It has already assigned it, the electron density, the given atom, and we will refine it to get the good agreement of R factor, so that we can say that the structure that we have created closely resembles to the real structure. So if we use shellxs intrinsic shellxx program and start solving it again, it will give us like this. This is the real electron density diffraction pattern. So with associated with each electron density, we can suggest the atom that it is a planar 6 atom 6 electron density, which is planar, which we can consider it to be the carbon atom. So we will associate it with the carbon and refine it. So it starts refining it and give us a particular value of R, and which is a 30%, which is very large. And obviously we have not solved it quite right now, so I will just do it assign the atoms, and it will start assigning it on its own, and it will give us a structure like this, which is obviously not right. Okay, so it is not quite right structure, so we'll start to refine it. Okay. So by clicking, I just deleted an atom, and let's start to refine it and see the impact on the R value. So the R value increases. Okay, so it is not in increment, so we will start to refine it. Okay, so this atom, if we consider it to be nitrogen, this atom to be carbon, as you already know, the structure of this is hydrochlorothiazide structure, so we will just assign the atom as we know. If we'll call it sulfur, we'll call it nitrogen, we'll call it chlorine. So now just refine it and see the R value. The R value goes from 22% to 7%, so it is in very good agreement with the real structure for now. If we now add hydrogens to it, so it will give us a structure like this. Let me just double check it. Nitrogen, sulfur with 2 oxygen, sulfur with 2 oxygen and 1 NH2, and a chlorine. Okay, and we'll refine it again. It will give us a refined structure with the new R value, which is 7.27. Okay, there is still some changes that is needed to be done, like a oxygen atom cannot have a hydrogen, and a nitrogen is supposed to have 2 hydrogens. Okay, And the nitrogen's hydrogen is kind of planar, so we'll assign this electron density as hydrogen. And let's refine it again. Refining it gives us a new structure with a good R value, but we'll just remove the hydrogen, refine it again, and then add hydrogen, removing a hydrogen from here, and making the atom ellipsoids. Why? So as to take the vibronic motions of the atoms within the lattice. And refine it again. It gives us a new structure with R value 4.61, which is not bad, it's good, but it is that nitrogen NH2, it's supposed to have two hydrogens. So we need to remove hydrogen, refine it again, there is no particular hydrogen density, we'll add hydrogen. Now it has two hydrogen, but it has an extra hydrogen, we'll remove it. We remove it, so it's just getting removed. We'll remove hydrogen, we'll add hydrogen. Let me just remove all hydrogen, refine it again. We will now add hydrogen, all the other. So finally the structure of HCT file has been drawn using olex, which satisfy all the chemical requirements, the valency requirements, and is in good agreement with the R factor, and the shift between the maximum peak minimum peak is also reliable. So we can say that the structure that have been drawn is very much closer to the original structure. Okay, so for the zip file we go to the refine, add, change the program to acta, and then refine it again. The the structure that has been drawn then converted into the zip file and be saved at the same position at which the HKL file of this HCT was present. Now using this Vesta software we will learn the how to that we have drawn the structure here, how to stimulate the XRD pre-XRD data of this structure that this structure should possess, and the unit cell of the structure. So we will go to Vesta, open the zip file that we have generated. This is the zip file. This should be the unit cell that it possesses. The unit cell can be seen as of monoclinic in nature, with one of the angle being non-90. All the sides of this unit cell, the unit cell length parameters, edge length, they are all non-equal. A not being equal to B not being equal to C. So this is the arrangement of the molecules inside the unit cell. We can see it closely, with red being the oxygen atom, the grey ones being the nitrogen atom, yellow one sulfur atom, and the brown ones are carbon atom, with the white one being hydrogen atom. So so after completing the refinement, this is how, using Vesta software, we can clearly visualize the three-dimensional unit cell and its packing arrangement. It allows us to see the simulation of entire crystal lattice, so that we clearly see how the molecules pack and interact inside the unit cell. Now it is time to finally, from the refined structural information, to stimulate the powder XRD, that is the X-ray diffraction pattern uh, simulation. So the PXRD pattern is extremely important because it allows the comparison between the calculated diffraction of pure crystal structure and the experimental powder sample. A good match confirms that the solid sample obtained experimentally corresponds to the same crystalline phase that we solve in the single crystal form. So to easily get the powder diffraction pattern from what we have created, the structure we have created, what powder diffraction pattern it should have, and for its comparison to the actual PXRD pattern that we obtain from the synthesized molecules, uh, solid molecules, we can see the degree of correspondence between those two, that how much they match, and whether we crystallize the required compound or not in the solid form. So in the utilities, we will go to powder diffraction pattern and click calculate. So this will give us the calculated PXRD pattern. So if the crystal structure we have synthesized in lab gives us PXRD data like this, like a peak at this point, and the intensified peak at this particular 2 theta value, and the other peaks at these obtained values. So if it gives the exact same PXRD pattern, we can say that we have crystallized the required compound. And if any of the one peak is missing or any extra peak is appearing, we can comment on the phase purity of the compound, that this compound is whether we have synthesized is pure or not, and how much it corresponds to the required structure. So this workflow, starting from the HKL and INS file, generating the electron density, solving the structure, refining it, exporting the report to other software. In this case, we have used Vesta, visualizing the unit cell and simulating the XRD pattern, provides a complete verification of the compound's identity and crystallographic purity. So as you can see, this is the already created that I have reported in this Word file. The time I was solving the crystal structure for all the three given HKL files, I have reported the PXRD pattern for the HKL file to be like this. And this is the PXRD pattern that I have for the structure that I have solved right now during the making, or during showing how the assignment I proceeded. So in this, the two PXRD pattern, we can see that there is a much similarity, or the PXRD pattern is the same. So we can say that these two compound is the same compound, and it is the same compound because we have used the same HKL file obviously. But we can see that the peak appearing here is here, and the peak appearing at this side is this side. The 20-degree value is at the 20-degree value, The 25-degree value, a particular peak is coming, the 25-degree value, a particular peak is coming. So this is how we can see the matching the two pxrd pattern, that whether the compound is same or not, or any extra peak is appearing on any each peak, a particular peak is disappearing, gives us a very important idea that how much is the purity of the compound that we have synthesized, whether we have synthesized the right compound or not. So the report from the olex file that we have created, the report that have been downloaded from this position, has been reported in the word file like this, which contains the identification code of the file, empirical formula, the crystal system that it belongs to, the unit cell parameters, the interfacial angles, volume of the unit cell, and other and other important informations. The radiation that has been used for the pxrd data collection and other things. The data collection, sorry, pxrd, the data collection that we have uploaded in that olex file, how much radiation was used, and what kind of radiation was used, and other things, and the unit cell parameter, the unit cell structure that which we have simulated using Vesta has been reported here, and the pxrd pattern. Similarly, the exact same way other crystal systems were solved for other files like ropa hkl. The empirical formula has been reported and other information has been reported, and this is the structure, this is the structure that look like during the solving in olex. And you can see that there is a good agreement in the r value, and this is how the interaction occurs between the two oxygens of the phosphate group and the two hydrogens of the of this particular big kind of moiety. Hydrogen bondings occurs, and this is how the unit cell that is from its file stimulated using Vesta, we can say that how we can see that how the molecule that we have created using olex is packed in a unit cell as done before. And the stimulated pxrd pattern using the same software, which is Vesta, the peak should appear for this if a compound is synthesized um, having this molecular formula. The peak should appear at these points, and we can check the phase purity. Similarly, for rmal file, very similar techniques has been used. We can see from the report we have created using olex software, so by solving and refinement of the structure look like this, we can see. And it has a monoclinic crystal system with these unit length, edge length parameters and interfacial angles, and the other information. And we can see that there is a good agreement of the r factor, which means that it closely resembles to the original structure. And this is the unit cell structure. You can see the symmetry, the benzene ring beside behind, and benzene ring behind another benzene ring. So this is the unit cell stimulated using Vesta for rmal. And this is the powder xrd data that should appear for the compound having this molecular formula. The peak should appear at these 2 theta values. So this is how we follow this to from getting the electron densities at a particular positions from the x-ray diffraction data, and using it to create the structure, and see its packing in the unit cell, and then its powder xrd to take its phase purity. This is how it is done, the complete interpretation of the data from x-ray diffraction patterns. So to conclude this study, this study demonstrates how the single crystal x-ray diffraction combined with olex2 refinement and powder xrd simulation, allows us to confidently determine and verify the solid state structure of a compound. Starting from the raw HKL data, we generated the electron density, build and refined the molecular model, analyzed the unit cell packing, and finally compared the calculated PXRD pattern with the experimental one. Obviously, we didn't do the experiment, but if we did, and we aim to synthesize this one of these drugs, the PXRD data should look like this, that we have simulated from Vesta. So, analysis of the unit cell and compared of the PXRD pattern. This complete workflow confirms both the identity and the purity of the crystalline phase. Overall, the process not only provides the structural insights at the atomic level but also validates the compound we synthesized is exactly the form we intended. Thank you.